Yeah, and thanks to the organizers for inviting me. I must say I've been up since midnight, so please forgive me if I get a bit loopy. Okay, so as the last two series of lectures have emphasized, a central enterprise in physics over the last several decades, over the last century, has been studying different kinds of phases of matter and the transitions between them. Okay, and while we continue to discover new and exotic phases every day, as a whole, we have many useful frameworks for thinking about equilibrium phases of matter. For example, we learned that ideas of symmetry and topology can play a big role in defining these phases, right? And we know that systems at high temperatures can generally look disordered, but at low temperatures, they may order by spontaneously breaking some symmetry, okay? So all of this remarkable progress is built on the framework of equilibrium statistical mechanics, okay? Equilibrium statistical mechanics allows us to make useful predictions about macroscopic systems with millions and billions of atoms or electrons or what have you, right? So just as any realistic experimental sample would have, okay? So in most textbook definitions or treatments of statistical mechanics, you have in mind a system. The system is coupled to some reservoir or bath. It's exchanging energy and particles with this bath. And as a result of this, it eventually reaches equilibrium at late times. And so what that means is that we can replace the detailed microscopic equations tracking the individual states of millions of microscopic particles with much simpler statistical averages over macroscopic states that are characterized by only a few parameters such as temperature or chemical potential. And then we can go into these macroscopic states and compute things like correlation functions, order parameters, topological invariance, and use those to understand the kinds of phases of matter we have in mind, okay? So for instance, if you were thinking about zero temperature, then you would evaluate these order parameters in the ground state of the system. But more generally, we could consider some finite temperature equilibrium state, such as the Gibbs state. Okay? So a major open question is, how do we generalize these ideas of universality and phase structure to the out of equilibrium setting? Okay? So this is comparatively far less understood and is a really active area of research right now. And in this set of lectures, I want to bite off a small chunk of this bigger program and consider Loci or periodically driven systems which satisfy a periodicity in time. Okay, and have a period which basically goes as that. Okay, because this system is now time dependent, energy is no longer conserved, okay? Instead, what we'll find is that the notion of energy gets replaced by something called a quasi energy that I'll describe, okay? But the usual notions of a ground state of matter or an energy gap, these cease to be well defined once energy is no longer a good quantum number, okay? So that's the first major change. And we choose the system to have this periodic dependence because the periodic dependence will actually allow us to nevertheless say some useful things, okay? Ideally, what you have in mind is a completely general unitary, right? So the most general setting is just a unitary for something like a system plus an environment, okay? And we can trace over the environment and write some effective time evolution for the system alone. And in general, this will be very complicated. It'll be non-Hermitian. I think you'll learn a little bit about this in the lectures next week, okay? So the problem in its full generality of how do you think about systems with most general time dependences is very complicated. But assuming this periodic dependence will allow us to make some progress along the way, okay? And I should also say here that, you could ask how is the system even getting this time dependence, right? So in a laboratory setting, of course, this time dependence comes from the system actually being coupled to some external environment. For example, you could be tuning the lasers in your system and using that to change what the different couplings in your system look like. But even though that is the case, we're still going to imagine that the effect of that environment is still to give us a Hermitian Hamiltonian, but it's just time dependent, okay? And what that means is that you can write down the dynamics of the system will still be defined by unitary time evolution, which is of this dependent Hamiltonian. Okay? So what this means is that the system can exchange energy with the bath, okay, but does not get entangled with it. Okay. So with this setup in mind, the plan that these lectures will follow is to start with single particle Floquet systems. Okay, so these are systems in which we can again think about independent electrons, like a lot of Joel's lectures. We'll use this to talk about Floquet block bands. And generalized topological classifications to the Floquet setting. Okay. So that's mostly going to be today. And then in the next lecture, I'm going to turn to many-body or interacting Floquet systems. Right. So one of the miracles of band theory is that you can write this relatively simple theory for non-interacting electrons, but this actually proves to be a remarkably good description of realistic experimental systems where, of course, your electrons have Coulomb interactions, and it's a genuinely many-body problem, right? So the reason this happens relies on ideas of adiabatic continuity, the notion of a gap, Fermi liquid theory, but all of those ideas no longer apply in the Floquet setting, okay? So in the Floquet setting, in going from single particle to many body, you really lose all the structure that you had in the single particle problem in some sense. One second. And what happens most generally is that your system just heats up to infinite temperature, okay? And the way you can think about that is that the equilibrium state that's relevant is the state that maximizes entropy subject to all the constraints in your problem. But when your system has time dependence, energy is no longer a good quantum number, so the maximum entropy equilibrium state is simply the infinite temperature state, okay? So there's really a breakdown in going from single particle to many body Floquet systems in a way that doesn't really happen in a static system. So we'll be addressing issues of Floquet heating and how this can be either prevented or delayed so that you can get non-trivial behavior for long periods of time. And we'll have to actually engage with how do we even define phases of matter in this many-body non-equilibrium setting. Okay, and this will introduce ideas of eigenstate order and dynamical phases. Okay. Then we'll put the two together and we'll consider a specific example, which is phases in a many-body Ising chain. This will lead us to the so-called time crystal phase, which is a phase of matter that only exists in this out of equilibrium setting and doesn't have any equilibrium or static analog, and we'll describe the properties of this phase, okay? So along the way, I want to distinguish between two kinds of Floquet phases that you might encounter. So the first is so-called type 1 Floquet phases, okay? So in this, periodic driving or Floquet is used more as a tool to get Hamiltonians and phases of matter that already exist for static problems, okay? So this is you can think of this as Floquet engineering in a way, okay? So this is a tool that's often very interesting in a laboratory setting where you want to engineer some interesting band structure, but the interactions or the systems that you have access to don't realize that in a natural way. But then you can drive it in some special sequence and get the kind of band structure or topology that you may want, okay? But the thing that we'll focus on more are type 2 flow K phases, which are, if you will, intrinsically flow K. And these have no static analog. Okay? So that's the plan. And there was a question?
Oh, yeah. You said at the beginning that was actually important that our design is drive periodic.
Mm-hmm.
But then you also said that we don't want, we want there to be Hermitian, namely that there is no entanglement between.
That's right.
For me, it's not clear why, so was the problem that we have if we still have a periodic equation,
Right.
but non Hermitian?
What's the problem that you have?
I mean, yeah, why do you want to have unity?
Oh, it gives us a way of, I mean, we still want to think about unitary time evolution, and it'll give us a way to answer many questions. So it'll give us this whole structure that we'll talk about. It's, of course, very important, very interesting to ask what would happen if you had a non-Hermitian problem and how to define phases in that setting. So this is all very, very open and very current. So but this is just, one simplification that allows you to say various useful things. And it's actually this is actually true in practice. There's all this effort that's been happening in the area of cold atom experiments to engineer isolated systems. And by isolated here, it's just, systems undergoing unitary time evolution. So they really, for long periods of time, they look like they're not getting entangled with some reservoir. So this is also, it's not just some, something of theoretical interest. It's also very practically relevant. Yeah. Okay. So, So I'll start with some simple flow K formalism that's really analogous to Bloch theorem. Okay, so in a periodic system, right? So if you have some potential, this is supposed to look periodic with some period A, right? So we all know Bloch's theorem. So suppose you have then we know that the eigenstates look like so this is the so-called quasi momentum, right? So because we don't have continuous translation symmetry, momentum is not conserved anymore, but it's only conserved mod, it's only defined within a Brillouin zone. So for instance, in one dimension, K lives between minus pi over A and pi over A, and this U of R is a periodic function of R. Right. So now instead of periodicity in space, or in addition to periodicity in space, we can consider systems that have periodicity in time, right? So what we want to dependent Schrodinger equation, which is I and you can show, just like Bloch's theorem, the solutions to this equation are the so-called flow K states or flow K eigenstates, and these take the form psi alpha t okay, and this is now a quasi energy, just like quasi momentum, and it lives in a flow K Brillouin zone, so it's only defined mod omega. So it lives from minus pi over t to pi over t, and this is periodic of time. Okay. So the proof for this proceeds exactly analogously to the proof for the usual Bloch's theorem. So once we have this, we know that these states satisfy various properties, and in fact, the time evolution of the system they form a complete basis for the time evolution. Okay, so the time evolution of any state can be expanded in that basis. And right now, I actually haven't made use of the fact that the system was, when I wrote Bloch's theorem for spatial translations, that was assuming a non-interacting single-particle wave function, but this is actually very general. Okay, so this could be a many-body wave function too. Okay, so we know that these Floquet eigenstates satisfy so they pick up this phase, and in fact, what you can very easily check is that if you look over a full period, right, this by acting with the time evolution operator over one period, and just plug this in and see that it satisfies that equation. Okay, so in particular, what this means is that the Floquet eigenstates can be defined in terms of the eigenspectrum of u of t, which is the time evolution operator over one period. Okay, so you can see that this is an eigenvalue equation. Okay, so this eigenstates of u of t we can denote by alpha, and the eigenvalues are phases. Right. So if you probe the system stroboscopically, okay, what that means is that if you go in and you look at the system at integer multiples of the driving period, okay, then all you need to know are the eigenvalues and eigenvectors of this Floquet evolution operator over one time period. Okay, so this is exactly analogous to a time-independent Hamiltonian. If you want to know the dynamics in time, you have the eigenvalues and eigenvectors of your Hamiltonian. You can take any state, expand it in that basis, and that's enough to give you the time evolution of any initial state. So likewise, if you probe the time evolution stroboscopically, all you need to know is the spectrum of this time evolution operator over one period. Okay, so I should also say that in general, you have not just u of t, but a family of time evolution operators that are all related by a unitary transformation, right? Because we can consider all operators, because the zero of time is arbitrary and actually represents a kind of Floquet gate choice. Okay, so if you want to know the evolution stroboscopically, you want to know, okay, am I probing the system? Where am I probing it between 0 and t? And then you look at this time evolution operator starting from that period. Okay, and these are all unitarily related. Which of course means that they have the same eigenvalues but different eigenvectors. Okay, so what's true now is that this Floquet unitary u of t can be used to formally define a Floquet Hamiltonian. Okay, and we can just define it. I'm going to call this u Floquet. Okay, I'm just going to assume that, let's pick the 0 of time t naught at 0. Okay, so this object is going to be called u Floquet, and I can use this to define a Floquet Hamiltonian, which is defined as so. Okay, so formally I can always do this, and H Floquet is a Hermitian operator. Okay, but actually I have huge freedom in defining H Floquet. Okay, so you can imagine that, if I've defined H Floquet in this way, yeah. No. So this is a static Hamiltonian. So this is not H of t. This is just the definition of H Floquet. So take the unitary operator. It's a time-ordered exponential. It's some complicated object. Just take its log. So you can always do this as a matter of principle, right? But the point is that this will not always be a sensible object. Like it's not going to be a local Hamiltonian. The things that we want to study are local time-dependent Hamiltonians, right? But this could just be a horribly non-local object that doesn't look like anything that you would write down in a good theory. Does that make sense? No, non-local in space. Yeah. So it's just so your Floquet unitary has an eigenspectrum, which is its eigenvectors. So you can always define this operator, and we'll consider cases where where this operator is sensible. Okay, so yes. No, so at this point, your Hilbert space has not changed. I'll talk about a different scheme later where the Hilbert space looks different. But right now, all I'm doing is, say U Floquet has an eigenspectrum. So you can define a change of basis. So it has eigen vectors V or alpha and eigenvalues e to the minus epsilon alpha, right? So you can define a unitary matrix where you take all these different alpha 1, alpha 2 as the columns, right? And then you can write H Floquet. You just have to take the log of this operator. So H Floquet is going to be P dagger, a diagonal matrix P. And what's going to live in the diagonal matrix is, so those were the eigenvalues of U. You want to take the log of those. So this diagonal matrix is going to be epsilon alpha. But now notice what happens. So epsilon 1, epsilon 2, epsilon n. But now, because these phases are only defined mod omega, right? So when you take the log, you have to have this choice, right? So that's your branch cut. So this has a series, you can put in any integers that you want. So your Floquet Hamiltonian is not unique, okay? As an operator, U well defined, okay? So any time evolution you compare with U Floquet is multi-valued. But if you want to think of it as a Hamiltonian, that's not unique. And in fact, it's not at all guaranteed that this operator that you write down will be a sensible local static Hamiltonian, okay? Good. Yeah.
Just last question. UF is just the time evolution capital T, right?
To time capital T, correct. Yeah, it's that object. Yeah. Okay. Yeah. Where you obtain what? Okay. All right. Yeah. Okay, so the question was, is our goal to diagonalize these new Floquet Hamiltonians? And not quite, because what happens is that there's going to be systems, where I talked about type 1 and type 2 Floquet systems, right? So there's going to be systems where this Hamiltonian is actually sensible. Like, you can go through this process and you can get a Hamiltonian out of it that actually behaves like a well-defined local static Hamiltonian. And then the phases that you'll get, our goal will be to define phases that you can get for this time evolution operator. So we're thinking about unitaries rather than static Hamiltonians. So that's the one conceptual shift, that we want to think about phases of unitaries rather than static Hamiltonians. When H Floquet is a well-defined static Hamiltonian, then the phases of that unitary will just be what you already had for that static Hamiltonian. So that's like type 1 Floquet. You don't get something intrinsically new, but you can use Floquet as a tool to engineer a desired H Floquet, okay? But there will be other cases where you really cannot write the unitary as the exponential of some sensible local Hamiltonian. And those will give us phases that are intrinsically new to the Floquet setting.
And in that case as well, it's useful to define what is Hamiltonian.
Sorry?
In that case, so we don't define that.
So you can always define it in this way. The question is, whatever object that you get, is it sensible or is it not sensible? How local does it look, right? I can always construct this operator.
I mean, when it's sensible,
Yeah.
it's useful as well.
Yes, because then you can just think of it as a Hamiltonian that you're very familiar with, right? Yeah. So that's why you do it, right? Because we're familiar with thinking about static Hamiltonians. So in cases where that works, you can just port all that knowledge over. But the new exciting thing will be when you really can't write it as a static, or when this object really doesn't make sense, that's when you'll get intrinsically new flow K phases. Okay. Good. So what does this get us, right? So for this non-interacting problem, we can go from the usual block bands that we had to flow K block bands, okay? And what that means is consider a one-dimensional periodic in space and periodic in time system. So you have K, which lives between minus pi over A and pi over A, and you have epsilon, but epsilon now lives between minus pi over T and pi over T, okay? So what are the kinds of band structures I can get, okay? So there's a boring answer, where the boring answer is just, okay, you get some, you get some bands that look just as they did in the non-interacting. So this is supposed to be, this value is supposed to match with that, okay? So when you had a static Hamiltonian, you drew a band structure, and sure, you've driven this system now, but your flow K band structure looks quite similar, okay? So that's one boring answer. This is when each flow K is sensible. But the new answer that we can get actually comes about due to a new topology that becomes possible in your flow K band structure. Okay, so usually your band structure has the topology of a cylinder. Okay, what you have is, so this is K. Okay, and you have some bands that may look like that. That's energy. Okay, so this is the periodicity of the Brillouin zone. But now your energy also becomes periodic. So this actually goes to a torus, okay, where this is the K direction and that's the epsilon direction, okay? And what this allows you to get is new kinds of dispersions that can wind around the torus in some non-trivial way, okay? So I'm going to try to draw this so you could have something like that, okay? And what does this get us? One striking thing that suddenly becomes possible. Usually we know that because of the periodicity of the momentum Brillouin zone, you know that epsilon of K has to be equal to epsilon of K plus G, right? But now this equality can be mod 2 pi because energy is only defined mod 2 pi, right? So for instance, we could get a band structure which looks like okay. So you see that this is K epsilon of K, okay? So if you had a static problem, okay, you could never get a band structure like this. Your energy is periodic, right? So that's why we get things like 2t cosine K, where it comes back to itself. You never get this chiral mode that can just go across the entire flow K Brillouin zone like that, okay? And what does this give you? You can think through if you have something like an average group velocity, right? This now becomes quantized because you see that this is giving you a net winding that you can't get rid of. You're winding in K space and you're winding in epsilon space, okay? So then your system has this average group velocity which says that the average displacement over one period is delta x is this group velocity times time, which is a unit cell. Okay, so this is really remarkable, right? So we heard in Joel's lectures that there's this notion of a Thouless pump, right, where you have some band structure and you can adiabatically deform the parameters in your band structure, and as a result of that adiabatic deformation, the system looks as if it's pumped 1 unit of charge, right, from one, say, from one edge to the other. Here, there's no adiabaticity, okay? So this is like a non-adiabatic Loci Thouless pump, if you will. Okay, because there's nothing adiabatic, but nevertheless, because of this non-trivial topology in the Loci band spectrum, it looks like over one period, your system can pump a quantized amount of charge. And we'll see an explicit example where hopefully this will become more clear. Okay, but that's the really new thing that you can start getting at the single particle level. Okay, so, yeah. Sorry? No, there's periodicity in space. So there's a momentum Brillouin zone. So that's why it's a torus, because you have a momentum Brillouin zone which goes from minus pi to pi, and you have a Loci Brillouin zone which goes from minus pi over t to pi over t. So this is the spatial lattice, and that's the time. Right? Okay. So any other questions? Okay. So in particular, what this a prediction of this kind of chiral edge mode, which is what it'll turn out to be. You can already see this chirality because you're really saying that there's this like group velocity which is positive. In this case, I can have an edge like that, in which case it'll be negative, and you're really pumping 1 unit of charge per Loci cycle. Okay. So this kind of chirality actually changes the usual bulk edge correspondence that we're used to, that Joel talked a lot about in his last lecture, for thinking about systems with an edge, for instance, right? So usually, if you have a static system, right? So say we have a 2D periodic system. Okay, so you have a kx and a ky, and you get some bulk bands, and you use these to define Chern numbers for the nth band. Okay, so then what we know is that if you now take this system and you open up one of the edges, so you for instance do something, put it on this infinite strip where this k parallel continues to be a good quantum number, but now you have these two in your system, right? So if you do something like that, and you draw your band structures, so you can have some band here, you can have a different band there, right? But what we know, so this is as a function of k parallel, this is epsilon, and this is the static case. Okay. So what we know here is that in the static case, there's definite lowest energy, okay? And then there's a definite ceiling to the energy. So if you go in and you write down what the Chern numbers for all these different bands are, say that's C equals 1, what we know is that the Chern number of the band is equal to the difference between the number of edge modes that lie above and below the band, right? So if this is Chern number 1, we know there can be no states below, okay? But then there's an edge state here, which then ends in that band, okay? So if you know what all your different Chern numbers are, you figure out what the different numbers of edge modes are, okay? So that bulk boundary correspondence, you can compute a bulk topological invariant of a system with closed boundaries. Now you open that how many different modes you have, that bulk invariant, okay? So this, as written, doesn't hold anymore within a Loci system, because you can now get these modes that wind around the entire Loci spectrum. Okay, so what you can get now in the flow K case is energy now becomes periodic again, right? So this is pi over t minus pi over t. And what that means in particular is that there's no floor to the energy, there's no ceiling to the energy, it's only defined mod 2 pi, right? So what you can have is you can have these two Chern bands, and these can have bulk Chern number 0, and normally if you have a system with bulk Chern number 0, and all your bands have bulk Chern number 0, that's just a trivial system. But this can have an edge mode that goes around the entire system like that. Okay? Because it's just, this band has one below and one above, so it's Chern number 0. This band has one below and one above, so it's Chern number 0. But there is still an edge mode that winds around the system. Okay? So what this is telling you is that in the flow K system, in the flow K case, simply looking at the Chern numbers of your bulk bands is enough to predictably tell you everything that you need to know. Okay. So one thing that I should clarify is how do you even what Chern number are we referring to, right? So you know that you have the flow K states that I'd written previously. T, right? So when you're talking about drawing a band structure like this, what you're doing is fixing a given K or fixing a given time, T equals 0. So in that case, these eigenstates are just the flow K eigenstates of the time evolution operator over one period. You can use these to compute a Chern number in the usual way. So you can, I guess there's also a band index here. So your Cn is just and okay. So what this is saying is that we had the flow K time evolution operate over one period. If you want to know the properties of your system stroboscopically, you look at the eigenvalues and eigenvectors of that object. But if you just look at the eigenvectors of u of t and use that to try to extract a Chern number, you can get very misleading information, or that information isn't complete because you can get all your bands have Chern number 0, but they still have this non-trivial winding edge mode. Okay. So what you have to do to really classify the system completely is to look at you have to, it's not just periodic in space anymore, but it's also periodic in time. And what you need to do is to actually look at what's called the micro motion of the system. That is, how does the system behave not just at time 0 and time t, but everywhere in the middle between 0 and capital T. Okay? So, so what ends up happening is, we have u of kx, ky, and t, right? But this u is periodic with kx, ky, and t, right? So what you can do is you can define functions that go from this 3 torus of kx, ky, t to the space of unitaries, and you can use that to define a winding number like what Joel was just discussing in his last lecture, which takes this motion within the period into account. So I'll define an object here, and I can tell you in a second what this is. Okay, so don't worry about the exact details of how this is computed, but the punchline is that you now have to look at something that's winding in kx, ky, and t, and pay attention to this micromotion operator. And this micromotion is just defined as when we had our u of t, we can equivalently write this as e to the minus I h flow kt phi of t, and this is now a periodic operator in time that quantifies this micromotion. Okay, so by adding this kind of extra dimension in energy, you can run all the same tricks and you can go through all the exercises that people have done for non-interacting band classification and get an expanded set of phases that you can get. And that's kind of this flow K, I'm just flashing this slide, is like a flow K Alkaline-Zirnbauer classification. So, usually if you have static non-interacting systems, you have all sorts of classes that are defined by the symmetries in your problem, like time reversal symmetry, charge conjugation. Those symmetries can now be defined with respect to the unitary, and you can use those and expanded and take into account this additional access that you have to get a new classification for possible flow K phases. Okay? Yeah. Yeah. This is a winding number. So this is an integer, and this ends up being equal to the number of edge modes. U is the time evolution operator. That's right. Yeah.
I see this winding numbers in space diagrams that the block states not being diagonal in the cable. So like not commuting with the translation operator not commuting with the time translation.
No, it's just periodic in kx, ky, and t. You just have an extra.
Right. Not independent. So can you see this diagram cuts as the two translations not commuting with each other, time and space?
No, it doesn't have to do with the commutation. It's just that, so if you had a system which was periodic in kx and ky, right, then you're going to have to take into account that full periodicity to get the full classification. You can't just ignore the ky, only look at kx and get the full story, right? So here, that extra dimension is provided by time. And in particular, it means that your bands can wrap in particular ways. So,
my block states,
yeah.
fix the time will not be the eigenstates of the flow K evolution.
Well, so it depends on what. So if you fix your time at time t equals 0, they are the eigenstates of the time evolution operator between 0 and capital T.
But not inside the time.
That's right. Not inside. Not within the micromotion. Yeah, if you look stroboscopically, then your flow K eigenstates end up being eigenstates. Exactly. Yeah.
I have a question.
Yeah.
Maybe this is too naive, but we say that we are studying the systems periodic in space and time.
Right.
So I would expect that instead of computing the integral over t,
Yeah.
maybe over frequency in the Brillouin zone of the frequency.
Well, so usually you have, right, okay, so right, okay. So you're saying usually this integral is not over x, but it's over, but that's because, so the thing that's, right, so we're not looking at our function between, right, so if you look at the time evolution operator over one period, right? Then this has this phase factor here with, its eigenvectors and eigenvalues are defined this way. So it's time is, when time is no longer a good quantum number, then energy is only defined mod 2 pi, right? So likewise, when space is no longer a good quantum number, momentum is only defined mod 2 pi. So that's the main picture. Yeah.
Okay.
Yeah. So yeah, that's right. Yeah, that's a commutator. Yeah. Right.
Let's assume that I have initial Hamiltonian, which is like 2 items and 2 items, 2 items.
Mm.
And now forget Hamiltonian has Loci Momentum. So
Mhm.
the previous size of the Hamiltonian. So in my initial logical space was 2, and now it is infinite. So what explains that this Hamiltonian contains essential and non-essential information. So can I somehow distinguish between them?
So I'll come to the repeated zone scheme that you're talking about in a second. You can ask the same question just if you have periodicity in space, right? You can think about your system as living within the first Brillouin zone, or you can think about the extended zone scheme where everything is defined mod omega. So that's the same spirit in which that's happening. But at least when I wrote it like this, as an operator, the Floquet Hamiltonian has exactly the same Hilbert space as the unitary operator, because it's literally just the log of that operator. Okay? All right. So I have an example that will be instructive, but maybe it's worth coming back to that after the break, because otherwise it'll take me a few minutes to set that up. Okay. Yeah.